Indifference curves can come in all sorts of shapes and sizes, and in order to know what they mean, it's often useful to look at some extreme cases first. In this graph, we'll look at the extreme case of perfect substitutes. We're imagining that I can't tell the difference between Coke and Pepsi, and so a can of Coke is exactly the same to me as a can of Pepsi. Similarly, if you give me 2 cans of Coke or 2 cans of Pepsi, those 2 bundles are exactly the same. So the 2 green bundles indicated here must lie on the same indifference curve for me. The same must be true for 1.5 cans of Coke and half a can of Pepsi, or 1 can of Coke and 1 can of Pepsi, or 1.5 cans of Pepsi and half a can of Coke. In fact, any combination of Pepsi and Coke that result in 2 cans should be exactly the same to me, and thus must lie on the same indifference curve. The set of all bundles of Coke and Pepsi that sum to exactly 2 cans can then be indicated by a green line that has a vertical and horizontal intercept of 2 and thus a slope of -1. This gives us one indifference curve from my indifference map, if it is indeed the case that I can't tell the difference between Coke and Pepsi. And just as I'm indifferent between any combination of Coke and Pepsi that sums to 2 cans, I'll be indifferent between any combination of Coke and Pepsi that sums to 1 can. All the combinations of Coke and Pepsi that sum to 1 can are indicated by this blue line that has a horizontal and vertical intercept of 1 and again a slope of -1. Of course, I'd much prefer to be on the green indifference curve than the blue indifference curve, because the green indifference curve gives me 2 cans of cola, whereas all the bundles on the blue indifference curve only give me 1 can of cola. I'll be even happier if I can get 3 cans of cola, and so we can draw a magenta indifference curve that has a horizontal and vertical intercept of 3 and a slope of -1, and indicates all the bundles of Coke and Pepsi that sum to 3 cans. I trust that you're beginning to see the pattern. When we have 2 goods that we can't tell the difference between, when they're perfect substitutes, the indifference curves will be straight lines that are parallel to one another and have slope of -1. Thus the marginal rate of substitution is equal to -1, which implies that you're willing to trade 1 can of Pepsi for 1 can of Coke, which makes perfect sense given that you can't tell the difference between the 2. If we were to measure cans of Pepsi as half cans and continue to measure cans of Cokes as full cans, you should be able to convince yourself that the marginal rate of substitution would become -2, and we'd get a map of indifference curves that are again straight lines, but now with slopes of -2. We'd still have perfect substitutes, and so it's not necessarily the case that perfect substitutes will always have slopes of -1, only if we get the units just right. The key feature of perfect substitutes is that the marginal rate of substitution will be the same everywhere in the indifference map.